Welcome students. Today we are going to discuss about dynamic characteristics. Already I have given some notes on dynamic characteristics, but that is not sufficient. So I have added some more notes to the dynamic characteristics. Before going to the dynamic characteristics, previously I have uploaded a video regarding the dynamic characteristics. One more important characteristics which we already discussed in the first unit itself. Again I am going to discuss here, that is hysteresis. And hysteresis effect, we can see the hysteresis effect in physical, chemical or electrical phenomenon, and it's going to explain as a different output effects when loading and unloading, whether it's a mechanical systems or an electrical systems. Hysteresis is non-incidence of loading and unloading of curves, and the two diagrams are indicated here. These two diagrams are indicating the hysteresis, which is shown. The first diagram is explaining the magnetic material hysteresis, and the second one is shown with the general hysteresis effects. Then the dynamic characteristics of the measurement systems. Number one, speed of response, measurement lag, fidelity, dynamic error. The speed of response. It is defined as the rapidity with which a measurement system responds to changes in the measured quantity. Okay, that is how fast the system is going to respond to the given input. Here the input is nothing but the measured quantity. The second one is measuring lag. Measurement lag or measuring lag. It is the retardation or delay, because we know that the lag is nothing but a delay in the response of a measurement system to changes in the measured quantity. Okay, that is if I am going to change some measured quantities. For example, if you are going to measure temperature, if I am going to introduce some, changes, and how fast my measurement system is capable of capturing that change in the measuring unit, that is changed in the temperature. So that is defined as measuring or measurement lag. Then fidelity. It is defined as the degree to which a measurement system indicates changes in the measured quantity without any dynamic error. So the second one and third one is almost same, but the third one is a degree to which a measurement system, just the rate is going to be different. Okay, only the definition is different. Then the last one is the dynamic error. It is the difference between the true value of the quantity and a measurement changing with time and the value indicated by the measurement system. So this is dynamic error. This is also somewhat closer to our true error. But with respect to time, if I am going to measure what is the true value and what is the measured quantity, that can be considered as a dynamic error. For definitions, please read all those given definitions which is taken from the prescribed textbooks. Okay. Then dynamic analysis of measurement systems. Actually, dynamic analysis can be done in two methods. One is time domain, another one is frequency domain. And the first one is regarding time domain. Time is independent variable, and input signal is applied to the system, and behavior of the system is studied as a function of time. That is how we are going to do this time domain analysis. And all this time domain analysis, frequency domain analysis is going to be repeated. You people are going to be repeatedly discussing all those things in your upcoming semesters. So it's very important. So learn clearly, understand clearly. If you are having any doubts, you can either message me or you can call, and we'll discuss what are all the things or what are all the problems you are having. Okay. So time domain, it is independent variable, and input signal is applied to the system, and behavior of the system is going to be studied as a function of time. A dynamic response of the system is analyzed at different intervals of time after the application of input signal. So this is exactly what is going to happen in dynamic response or dynamic analysis of the measurement system. Before entering into the time domain analysis or frequency domain analysis, first I would like to introduce the standard test signals, because this is the first time you people are going to get introduced about the test signals, and later we will be discussing about the same test signals in control systems and in DSP, that is the digital signal processing signals and systems. Okay, and even in computer control of process we will be discussing about. And for instrumentation engineer, without the test signals, definitely you are not going to, it is not possible to complete your degree. Okay, so this is so important. So what are the standard test signals? Step input. A step input represents an application of a sudden change. Example is also given, sudden rotation of a shaft, it is for a mechanical example, and sudden closure of a switch of an electrical circuit. And generally these test signals, how we'll be defining is, first we'll be generally defining about a step input or any test signal, then which is going to have a magnitude of A. Okay, then we'll be defining a unit step or unit test signal. Okay, this is general notation how we will be discussing about the test signals. So unit step function, RFT equal to 1 if t is greater than or equal to 0. Okay, if t is the time value is equal to or greater than 0, your RFT is going to have a 1 because it's a unit step function. And if it is going to be a normal step input, in the place of 1 will be having here constant value. Generally the constant used is A, the letter A. Okay, then RFT equal to 0 when t is less than 0. The diagrams are indicated here, the unit step signal and the step function of a magnitude A, which I already explained. I hope you can able to understand. So what is the unit step signal? RFT equal to A, where t is greater than or equal to 0. In the place of, as I already mentioned, the 1 and A is going to be replaced. Okay, and similarly the Laplace transform of a step input with magnitude A is also given, and you can expect some questions in 2 marks. For these kind of questions you can expect in 2 marks, and this is very important because this is basic, and I have given a MCQ quiz. Definitely you might be you have to know all these things, then you can able to answer the quiz. Okay, answer the quiz. Okay, then the next signal is ramp input. Ramp input is also called as a velocity function. So this is an activity of 45 degree line which is drawn between the x and y signal, and mathematically R of t equal to AT for t is greater than or equal to 0, and it's equal to 0 for t is greater than or equal to 0, and Laplace transform, LT is nothing but Laplace transform for R of s equal to A by s square. Then if A equal to 1, it is called as unit ramp input. I already explained you. Okay. Then parabolic input, this is acceleration function. Then parabolic input, R of t is given by AT square by 2 U of t. Now R of t equal to AT square by 2 for t is greater than or equal to 0, and it is 0 for t less than or equal to 0. Then Laplace transform of R of s is also given, and if A equal to 1, then that becomes unit parabolic function. Then we have the impulse input. It is the input applied instantaneously for short duration of time of very high amplitude, which is shown in figure. And example is sudden shock, that is high voltage due to lightning or short circuit, and it is the pulse whose magnitude is infinite while its width tends to 0. That is t tends to 0. So what is the input? R of t equal to A for t equal to 0. Okay, this is important difference. At t equal to 0, at that moment, that is if time becomes 0 only, will be having R of t equal to A or R of t equal to 1 if it is a unit impulse signal. Practically speaking, the impulse signal is not possible because at time t equal to 0 it is not defined, but the sudden shock, any sudden shock or sudden close of the electrical circuit or high voltage utilizing, that's going to exist only for a moment of time. Okay, that for a very lesser period of time, very lesser period. So that kind of timing is considered as impulse time. Okay, is it clear? Okay, within a fraction of a second that's going to happen. That's why we have taken it as a t equal to 0 and t equal to 0. Very clearly you have to remember and you have to understand. At t equal to 0, R of t equal to A, or if it is a unit impulse, then the A is going to be replaced by 1, as I already mentioned. And for all other values where R of t is going to be 0, that is if time t is not equal to 0, then what is my input? My input is going to be 0, right? And here the last one, the table is indicated with the standard input signals and its Laplace transform. It may be a summary. Okay. Okay, transfer function. I will once again I'll continue this one. So LT will be defined by an nth order differential equations. The differential equation is given here. an minus 1 and up to a naught are going to be the coefficients, and similarly b naught, bm are constants, which represents a combination of system parameter, and then your differential equation is shown here, and c of t is going to be output variable and r of t. So you can able to see here the c of t is connected with the left side of the equation and r of t is connected with the right side of the equation. So c of t is going to be the output variable and r of t is going to be the input variable. A naught, a1 to up to an and b naught, b1 up to bm are constant, which represents the combination of system parameters, and with taking Laplace transform on both sides, assuming all initial conditions equal to 0, then the equation becomes an Sn plus an minus 1 into s power n minus 1 up to that is going to be in left hand side and right hand side similarly, bm sm plus bm minus 1 s to the power n minus 1 etc. plus b naught into r of s. Okay, because we are going to take the left hand side is going to consist of c of s and right hand side is going to consist of r of s, and then if I am going to define my transfer function g of s equal to c of s by r of s, that is Laplace transform of the output divided by input is called as transfer function, and m should be less than or equal to n. Okay, then the block diagram representation, output is c of s and input is r of s, and g of s is a transfer function, and we know that g of s is output divided by input, then output is required in the sense c of s equal to g of s into r of s. Then time to rate response. The type of the input signal cannot be known fully ahead of time, as in almost in all applications. The signals are random in nature, so the time to rate response of the measurement systems is studied with the help of standard input signal like impulse, step, ramp and parabolic. So this is the exact definitions of the time domain response, and this is the importance of the standard input signals which we discussed earlier. We move on to the zero order system. A zero order system or zero order instrument is one where the highest order of the derivative describing the system behavior is 0. Okay, highest, I'll repeat, the zero order instrument is one where the highest order of the derivative describing the system behavior is 0. So a naught, only we are going to have a naught and b, a naught in the left side and b naught in the right side. All other constants are becoming 0. Okay, then a naught c of t equal to b naught over of t, c of t equal to b naught by a naught over of t, c of t equal to b naught by a naught r of t, and this is called as s equal to b naught by a naught, so c of t equal to s into r of t, and the example is linear potentiometer, and this is an important 2-mark question, so please make a note. And a potentiometer, a part that is a resistor which is connected in both end and also its sliding contact is also connected. This is called as a potentiometer, which is used as in used to divide the voltages. Okay, the applied voltage is going to be EI, and using the sliding contact I can able to connect only a lesser amount of voltage to the output. Okay, so that is the difference here. This is EI and this is length of the potentiometer, and here will be going to have, based on the displacement, the voltage, only this amount of voltage is going to be connected to E naught. Okay, you can just please check the PPT I am showing here. Okay, then this is going to be the output voltage and displacement XI graph. This is going to be linear one, so this is the example of your zero order system. And just continuing with the zero order system, C naught of t equal to EI by L into Xi of t, which is equal to S into Xi, that is equal to EI by L voltage per unit length. Okay, we move on to the first order systems. Actually, the first order systems in all the physical systems, like for example, mechanical, liquid, thermal, electrical, you'll be having so many first order systems. Here, I'm going to show the electrical based first order systems. If you're going to refer the book, you can find all the other physical systems also. So for RC, I'm explaining here. Okay, for RC circuit. Similarly, you can do it for RL also. I have taken the example of RC alone. Right. So this is the circuit given, and the basic equations is also given. And if you are going to write the equation, that is applying current KVL or KCL, we can able to write this equation. EI U of t, because that is the input, which is equal to the resistance R into I of t plus 1 by C integral of I dt. That is, I am writing the voltage KVL equation here. The basic fundamental equations of capacitor is also given here, right? Okay, taking Laplace transform, EI by S equal to R into I of S plus 1 by C is I of S. Then just doing some simplifications, we'll be getting what is I of S equal to EI by R into 1 by S plus 1 by RC. And then taking inverse Laplace for this equation, okay, for this we are taking the Laplace inverse Laplace transform of t equal to a by r into 1 by s plus a. This is right. Okay, for this you might be knowing what is the Laplace, inverse Laplace transform. This is nothing but e power minus t by rc. And the rc can be considered as a time constant tau. So tau time constant is equal to rc. Then I of t equal to the, again once again the equation is written here in terms of t and tau. So therefore I of t equal to ei by r and e power minus t by tau. And the plot of current I versus t is shown in figure B. The current decays exponentially with time. Okay, then the voltage across the capacitor, the EI, is also shown here, which is increasing linearly. That is shown in the figure A. We are going to consider the voltage across the capacitor, that is E naught of t, which is equal to 1 by C integral of I dt. Differentiating, we will be getting d by dt of E naught of t, which is equal to 1 by C I of t. I of t from the previous equation, you have to substitute it. Then finally, we will be getting, after substituting and doing some simplification, we will be getting this equation E naught of t equal to EI by RC into e power minus t by RC, right? Then taking Laplace transform for the above equation, we will be getting S into this one. Okay, this one. S into E naught by S, which is equal to EI by 1 plus SRC. Then E naught of S equal to EI by S into 1 plus SRC, which is equal to EI S into 1 by S tau. Then by factorizing, because we have to solve this equation by factorizing, left hand side I am going to have EI by S into 1 plus S tau, which is equal to right side I can write EI by S plus B by 1 plus S tau. Okay, and how we will be finding your A value is nothing but A equal to cross multiplying it, A equal to 1 plus tau into EI of S divided by S into 1 plus S tau. So this is S and S gets cancelled at S equal to 0. So EI is going to be there in the numerator, and if I am going to substitute S equal to 0 in the denominator, then I will be getting just EI. So therefore A equal to EI. Okay. And similarly we have to find what is B. And for B, we will be substituting 1 plus S tau equal to 0. So S tau equal to minus 1, which is shown here. This one, okay, this one, 1 plus S tau equal to 0, S tau equal to minus 1, therefore tau equal to minus 1 by S. So this is the value for which we have to substitute for S. For B equal to EI, that is cross multiplying, like in the previous case, EI by S into 1 plus S tau in the numerator, and the same in the denominator get cancelled. And for s, I have to substitute minus 1 by t, which is giving the value for t equal to minus ei tau. So now we have to substitute these value in the equation. Okay, we'll be getting ei by s minus ei tau by 1 plus s tau. Then taking the Laplace transform, e naught by s equal to, e naught of s equal to ei into, that is taking ei as a common, 1 by s minus tau by 1 plus s tau. And for this equation, we have to take the inverse Laplace transform, therefore e naught equal to ei into 1 minus e power minus t by tau. And this variation already, the variation of the voltage across the capacitor, which is already, the diagram is given in the previous page itself, but incidentally has given here. This is the how the voltage across the capacitor is going to vary, e naught equal to this equation, okay, ei into 1 minus e power minus t by tau. Okay, this is the general equation for the first order system. In general transfer function equation, all a's and b's other than a1, a0 and b0 are taken as 0. Then finally I'm getting, that is in the previously we introduced, starting with the transfer function, we introduced this equation. So now this becomes, for first order, this becomes a1 d by dt of c of t plus a0 c of t, which is equal to b0 r of t. Okay, this is the first order system. I am dividing the equation 1 by a0, will be getting a1 by a0 into p c of t by t of t plus c of t, which is equal to b0 by a0 r of t. And a1 by a0, we are going to take it as a tau time constant, and b0 by a0, we are going to take it as a es. Okay, this is static sensitivity and tau is time constant. This is equation 2. Then taking Laplace transform of equation 2, will be getting tau is c of s plus c of s, which is equal to s into r of s, and taking c of s as a common, then I will be getting 1 plus tau s, which is equal to s into r of s. Transfer function of first order system is g of s, which is equal to c of s by r of s, which is equal to, that is manipulating or taking this r of s to the left hand side, c of s by r of s, which is equal to s by 1 plus tau s. Therefore g of s equal to 1 by 1 plus tau s, dimensionless transfer function. So I am going to take s equal to 1, this is equal to, numerator is equal to 1, then this is going to be a dimensionless transfer function. Okay.